have Cerqueira Fernandes here, who's going to give us a talk on ROS2, basically on how you go from the operative ROS1 to the operative version of ROS2. Okay. Jose is an engineer in the National Robotics. He's working in robotics projects at the moment. He did his MN here at Heriot-Watt, but he is from the computer software engineering side of things. So you're going to see the differences in when he does the programming and set up his environment. So he recently migrated to robotics, so now he's working in a lot of robotics projects, and he's working a lot in ROS, so he's got a lot of experience in the past year working on it, so he's going to tell us a little bit about what he's done, okay? So thank you, Jose, for talking.
Good luck. Thank you so much, Ignacio, and also to thank Ivan as well, because he was also important for me to be here. So, as Ignacio said, I come from the computer science field, and this presentation is really like a perspective from a computer scientist into the ROS system. So, just a brief outline. So I'll just go through the history and the initial architecture of ROS. I'll then go and then also talk about the version 2. One of the really good components of version 2 is data distribution system. And after that, I'll be comparing ROS1 and ROS2. Following that, I'll be showing you the development environment on how you can get started, and then I'll do a demonstration. I'll try to do two demonstrations. One showing more what is the workflow that I have working with Docker, and then I'll show how you can work with Gazebo and RVs in a real project. So, as I said, thank you, Ignacio. So, as Ignacio said, I recently graduated from the Masters of Software Engineering, and I'm a junior software engineer at the National Robotics. I've been involved in some projects and some contracts that are ongoing, and I have recently started my ROS journey, focusing more on ROS2. I believe in its potential, and I would like to focus on data engineering, data science, and machine learning aspects of robotics problems. And I'm also looking for contributing to ROS2, because I believe I can do some good contributions. So, funny story, when I first, as I told you, I come from computer science, I didn't know anything about robotics, so I was just still trying to get the names of everybody within the team, and I just kept hearing ROS, ROS, ROS. Like, after the second day, because so many acronyms, I asked my colleague Ari, I was like, who the hell is ROS? Like, he's always involved in all these projects. And then he was laughing and said, no, like ROS is just a system. And yeah, this was a funny story. So I was already interested in learning, because I was like, yet another operating system. Like, and for robotics, like, why? So just a brief overview of the history before ROS. Any industry demands standards, and robotics is not an exception. So the main issues initially would be is the modularization, which is very important. Portability, being able to take code from one machine to the other, and also the communication within the systems and between different systems. There is a characteristic of robotics engineers that is both amazing but also not as good, because roboticists are very resourceful. So they know all about mechanics, computer science, and so on. So they have a tendency to reinvent the wheel, because they have capacity to work in many different fields, because it's a multidisciplinary field. So all of this produced in the beginning unmaintainable systems because you would have to try to connect all these components that were not standard, were not developed in a standard way. So I'll now give the definition of ROS, my personal one. So I think it acts like as a meta operating system for robotics. So it's, in practice, is a full-feature robotics framework that implements a communication protocol layer. It provides a runtime so that nodes can talk to each other, and a package management so that you can reuse standard functionality across many projects. So, from my research and talking with people, ROS was a great success, especially for the great tooling, great capabilities, and the extensive ecosystem. But I would like to focus more into a computer science perspective because, in my opinion, it follows a lot of what is Unix philosophy. So Unix philosophy is about simple interfaces, components that are loosely coupled, and is highly composable. So these are traits that you can see in every good system. And like when I first learned about Linux and everything, I was like, this is really basic system, like everything is a file, like a device is a file and a USB is a file, like that doesn't make any sense. But it's exactly because of that that is a standard for computer science. And ROS attempts to be the same and effectively is. So the architecture of the first version of ROS is based on Linux, the operating system, and re-implements TCP and UDP networking protocols. Above that, you have two different software libraries, ROS2, which is in Python, and ROS1, which is in C++. And then on top, you have your code. So, one thing that I can point out immediately is like two different software development kits, ROS2 and ROS1, that have different development tools and different capabilities. So they are not consistent, and in a project, it forces developers to jump from one language to the other, and the goal is really for you to not be as constrained. So this gives more freedom to the developers. So I would like to do a quick break and ask the audience if you notice anything wrong, and I will point out the topology. So, anyone? This is good. What do you think?
I think it's like forced implementation. Is it standard like documented like in a LaTeX file where you can implement it in any language that you want to? Or is it just an implementation and everybody has to use like one repo out there?
That could be one of the downsides. Thank you very much.
Something that's meant to be distributed, so across multiple platforms has a single cause or a single point of failure.
Exactly. So that's really good. And yes, so the centralized topology represents a single point of failure, and this is very important because if you have a central node, you can very easily, for example, do a DDoS attack. If you want to stop a robot, you just flush the memory with millions of requests, and your robot will stop. So this is really bad. And also, the master node routes all the network through it. So it acts like as a master, but in reality is really a slave because it needs to work for everybody, and that causes network congestion. And due to the network congestion, you have process queuing. So there are many robotics many robots in the industry that have this problem, and they are now trying to move from ROS1 to ROS2 because of performance only. So really poor performance. So as I said, networking, we have the network congestion, and because this was re-implemented, this forced the nodes to do remote procedural calls to each other, like through the master. So that's not really scalable because it's very imperative and not declarative. So you need to specify the steps to communicate from one node to the other. And also, the node discovery was inefficient because it needed to go through the master. So we always go back to the synchronization problem. So all of this was difficult to scale, and this actually goes into what we were trying to avoid in the first place, to reinvent the wheel. So we don't want to reinvent communication protocols. So now let's go on and talk about ROS2 architecture. And let's see how it improves things. So, first of all, now it's cross-platform. I personally don't like that, because that just adds like more abstractions on the bottom layer. And Unix is a standard, so I don't know why we need to do it. Then you have a data distribution service, which is a really good communication protocol, which I will briefly talk about. We have now redefined the communication, not the networking, but the communication protocols into services, topics, services, and actions. Also, the SDKs are now architected in a different way. So you have a C library that implements all the capabilities. So all the capabilities come from RCL. And in terms of building, you have a MENT build system that is on top of CMake, and Conquer, which is a command line tool, which makes everything more pleasant. So, as I told you before, Unix, simple interfaces, highly composable, and loosely coupled. So that's encapsulated in the node. So it performs a single task and takes constructor arguments. So this encourages people to reuse nodes, which is really good. And it's a declarative paradigm, because you can treat this node as a function and just add more parameters and be more descriptive about what you want from each node, and maybe just write one node that does 10 different functions depending on the argument. So this is fantastic, and this ties into what the Unix philosophy is. Then we have the topic, which is a broadcast streaming protocol. So it's really a connectionless communication in which the publisher sends message to topic. But here topic is not a component. All this has to do with data distribution service. So it just sends it in that direction, and the subscribers, they are listening from that topic. So publisher and subscriber, they are connected to that topic. So this allows one-to-one, one-to-many, or many-to-many types of relationships in this communication. Service. So this is a connectionful communication, because one node needs information from another node, and it will require the other node to confirm the data, and which is different from the topic where you don't care if you get the data or not, because it's a stream. Just pick it up when you can. So the client and the server are nodes' internal components, So that's already inherited in the ROS node superclass, and the services are also, they run asynchronously. So they have non-blocking execution. So maybe perhaps somebody has used Node.js, and it takes influence from Node.js in which it will not stop execution, it will just leave a thread waiting, but then it will continue execution on other threads. So that's really good, and a server can serve one or multiple clients. So, action. So this is a communication protocol for goal-oriented tasks. So this is an aggregation or a composition of two services and one topic. The action service requests the execution or the cancellation of an action. So initially it does the request to execute, and if something is wrong, it can also send a request to stop the action at any moment. The feedback topic does stream the progress from the node doing the action to the node that has requested the action. And finally, the goal service acts as a fallback for the node that requested the action to get more information about the state of the action. The topic may send a simple string about a specific about some specific data, but the goal service gives a better, a more extended set of data in case of completion, and if it fails, it can request a report about what happened. And now the C library. So it implements all the API functionality. It's written in C, which is used for 50 years, stable, and serves minimal higher level libraries. So this is where the improvement comes from, in which you don't have different libraries trying to implement different features and different capabilities, but you have like a solid and robust base layer, just like a kernel, let's say. And now it lets the ROS framework to be truly language agnostic. So I believe as a software engineer there is no perfect language. So it's like a tool, like any other tool. So you pick the best tool for each problem. So that's a huge improvement because you can bring a lot of innovation from different languages and a lot of power from languages that are older and they are more lower level, for example. So that's really good, and that will add more disciplines of computer science into this field to make robots even more intelligent. So I'd like to now ask the audience, like anyone, like what are the advantages of distributed systems, if somebody can pick up like some advantage.
No point of failure.
Oh, yeah, that's good. Another one, please.
You can take some load off of small IoT devices and put it in a centralized system.
Very good, exactly. And you can see there are not many Bitcoiners around. But yeah, so it just makes everything more efficient. Like if you see like a pattern in systems as they upgrade and get better, they tend to be decentralized and to use this kind of consensus algorithms and stuff like that. to accomplish scale. For example, in Google and stuff like that, they use distributed systems to elect which node is the best to process a query, and they start building, so they cannot have a node responsible for one task, and instead they have loads of equal nodes that decide between each other which one is going to take the task. So that's where ROS wants to be as well. So finally, data distribution service. So this was a great upgrade on the communication, because now the ROS developers don't need to think about networking and communication, lower level communication aspects. So they can focus on robotics instead of being network engineers. So that will make everything more robust, because they don't need to maintain that. So it's a set of protocols on the OSI network and hardware level, and it's designed for real-time and embedded systems. And as you can see, it's already used in transportation, infrastructure, and military industries. Like, for sure, modern cars use this under the hood to communicate, like to have all the different components, digital components, to talk with each other. So definitely they are using a data distribution service, and ROS wanted to integrate that into the framework. So it's data driven. Instead of doing remote procedure calls every time they need data, they instead capture other nodes' state through snapshots. So the nodes, they just broadcast their state in a generic way, and then each other node will collect the data from this bus and get the data that they need. So it's a declarative interface. So it's going to scale better in terms of development. It's transport independent, because it routes data through the network or shared memory. If two nodes are in the same computer, they don't need to be routed through a master node, for example, or through the bus, because DDS is excellent way of making real-time and embedded systems, and I would like to ask the audience why it is, judging from the diagram, if somebody can speak about it. What is the topology you identify from there?
What's topology?
What's topology?
I think so.
Perfect, exactly. So this is, in reality, this is a bus. This is a virtualized bus over the network and hardware layers of all the nodes that are connected to it. So there is no routing. This is super fast. It's just like a river. And this river has data streams from all the nodes. And then each node individually just filters out the data that they are looking for. So there is no more routing. And this is why this accomplishes like peak performance and reliability. So this is really, really important, that this is a bus topology system. And it ensures that all the nodes use the great quality of service policies when they join. Data distribution service determines what is the best policy, because it's implemented separately from ROS, and it's shared across industries, and provides efficient node discoverability. So this works like other networks where when you join the network, you just broadcast your existence for a limited period of time, and then all the other nodes will pick up that individually, so in a distributed way again. So, in reality, every ROS2 application is a DDS application. So this makes so that any robot can connect with any embedded system in the industry. So ROS now it's capable of, for example, being in the military, for example, and other high precision industries. So it's interoperable with any of those. It's open data model. So many industries, they are reaching a consensus on what are the data types that are important in embedded systems. So that leaves that burden out of the ROS developers, because it's like industry agreed. And it's the ROS data language when you are producing applications and communicating between different nodes. So as I said, peak performance and reliability. So this is the greatest upgrade from ROS1 and ROS2. This changes everything. So I already spoke about a lot of the advantages, but maybe someone else could add something else, if you think.
Can I ask a question? You said ROS2 is a bus topology, right? So if you're sending data and you're sending it to multiple nodes, right? It's not sending it like node 1 to node 2, node 2 to node 3. It's like node 1 is sending to all of them together, but that's not like a bus, right? That's just a broadcast. More like...
You can understand it that way, but maybe it's not the best way to explain it. It's broadcasting because it's putting it in the stream, and all the other nodes have connection to that stream. It's not technically, you pointed out correctly, broadcasting, but it's putting the data into a vehicle that all the other nodes will be able to get the data from. So that's actually a fair point, to be honest. So it's not broadcasting, but acts and behaves like a broadcasting. It's like, and then this is my comprehensive comparison. So DBS and RCA for me are really the greatest upgrades, and puts to shame old ROS1. So I'd like to do some notes about migration and interoperability between the two versions. So ROS1 distributions are phasing out. There is still one or two ROS1 versions that are still going, but ROS2 has been active for a long time, but it's still maturing, but reaching the end of ROS1, we will reach it very soon. And the interoperability is granted by ROS bridges between like ROS1 and ROS2 and vice versa. So now let's talk about development. So we'll just define how to get started and now the main components of a project. So executable. It's the program that runs the node effectively, and it's executed from a package. The launch file can trigger a single or multiple executables and sets the parameters at runtime. So the launch file is really the tool that you can use to make highly composable systems. Package. It stores every program and contains the program's metadata. You have some of these components that describe how the metadata, how the package is built, and what are the scripts installed, in this case for Python. The examples I have here, they are all for Python, because it's more accessible for a white audience. The workspace, it's like the place to develop all your packages and to execute commands. And you have two workspaces, the system that has the runtime packages, and the local one where you develop and integrate your packages. So the building tool you have for the building tools you have Amend build system that has the advantage of building it for different languages, and it uses the XML file format to do the description of the builds. Colcan is like a command line building tool, and just allows a simple interface between user and ROS. So I'll now just go like quickly through because I'm pretty sure Ignacio already explained a lot of how to get started. And then I'll do two brief practical demonstrations so that you get a feeling on how to develop using Docker. I will say using Docker. So to create a package, you create the workspace folder if you don't have it, and then the difference between the command line tool between ROS1 and ROS2 is this. So from the computer science point of view, this is an upgrade because it is separating, decoupling the name of the program, ROS2, from the verb or from the namespace or verb. So that makes it easier to interact, because if you don't know something, you can go ROS2 -L. Instead of in ROS1, you would have to go and see and know the enumeration of all the different namespaces and commands that ROS1 has. Now everything is within this program, and then it's then decoupled into namespace. So this is a namespace actually. So namespace package, and then the verb. So this looks like something that is insignificant, but this makes a huge difference into your workflow. So this is really good. Then you have the name of the package, and then you have to select the build system, if you're using Python or any other language, and dependencies. So that's nice because you don't need to tinker if you already know what are exactly the packages you want the dependencies you want. And then, I don't know if ROS1 has, but Conquer allows you to just build the package you want. So maybe sometimes you have huge projects, and instead of building huge programs every time you want to test, you can just select the one you are working on or you are changing. In terms of code, there aren't many differences into the software interface. You just initialize the superclass, the node superclass, and you pass on the name of the node. And in this case, we're just doing hello world, so that we signal when the node is created, and we pass this into the SDK. We pass the arguments, and then you also need to be, you are responsible for destroying the node. So this is very, very important, because even in Python, as you can see, you need to release the resources. So you could say that this is a drawback, but this is actually an artifact of making this more agnostic, language agnostic. So this is how this is the reason. But this is good because you want to be language agnostic. And usually in Python programs, you don't need to worry about releasing resources, but yeah, for the sake of the Python library, be minimal and be on top of a solid C library, you have to do this. So in my opinion, is good. And then now you have the launch file. So this launch file is the file where you can do the composition and make really complex and elaborated applications. So you have like always package, the name of the executable, the output, if you are doing it to the screen, and then I didn't have space in this slide, but you can add additional arguments, which are the arguments for the node itself. So it will be after the output, you do comma, and then you put all the runtime arguments. And nothing new here. It's essentially the same thing. You export humble, and then you source the runtime environment, and then following that you export your development environment. So there is no change in here. And then you either execute, you run the executable or the launcher. I'm not sure if in ROS1 is the same or different. So now is the demo time. Is something will break, I'm pretty sure. But before I go into that, I'll do some considerations about the state of how you develop in industry, because there are still some incompatibility issues at hardware level, drivers, Ubuntu versions, and ROS versions and ROS tooling. So adding the transition of ROS1 to ROS2 just exponentially increases the complexity. So the best solution is to use Docker. So within Docker you have an instance of ROS, and within that instance of ROS you have all the nodes running, and then you need to create different Docker instances to run some other programs that are not compatible with your initial ROS instance. So sometimes you need to use ROS1 because there are still some tools that are not mature enough to make it into the stable version of ROS2. So ideally, this will be less of a problem once that this transition is complete. Also, NVIDIA is big in artificial intelligence and robotics, gaming, and all of that. So there is a big dependency on NVIDIA for robotics applications, because they have invested a lot into that. And in development environment, please don't use Wayland. Okay? I know that Wayland is great. I'm not interested yet in it because it's not a standard yet. It might become, but the standard for the last 30 years or 40, I don't know, it's X11 in the Unix systems. And when you are working in Docker, the Docker needs to be integrated with the NVIDIA drivers, so that has access to the GPU, and also needs to have access to your desktop. X11, by the way, sorry. X11 is a desktop server. So it, when, for example, we have a graphical interface, thanks to X11 that acts like, I don't know very well how it acts, but just provides this graphical interface for all the graphic applications you have. So we need X11 in development stage, and I will demonstrate that shortly. And also, while I was researching how to install NVIDIA in Linux, I came across this curious fact. And just in case, like somebody really like the movie, so. And I love NVIDIA. I love NVIDIA. And also, so first of all, the demonstration I will do, I have chosen Usayo, which is it's an organization for robotics. They have their own robots, their own tutorials. So I chose a tutorial that you can do it yourselves very easily, and I will demonstrate how. And also my dot files. So I mean, I use Linux, so the killer functionality for me in Linux is like the capability of having my configuration, my workflow in any Linux computer, because I have a repo for all my configurations. So I will also show my Docker shell scripts that I use in production, and I will leave everything here available for you in case you want to use. If you want to install my dot files, I can help you. I don't have any README, I apologize for that. But if you like email me or something, I can help you out, and I actually can do a README. I just didn't have time, but please bear with me. But I will show you a quick way for you to install the scripts I have to work with a single Docker container to develop on it. So perhaps perhaps I will go first to my dot files. So as you can see, it might slip because I've been playing about with all of stuff. So this is like not related, but all my configurations are here, and I have configurations for a lot of stuff. So the link I gave you takes you directly to this folder, which is a script. So in reality, if you git clone, or if you fork, you should fork. If you fork my dot files into .config, then you can go to your bash RC. This is recorded, so you can then do it. So if you git clone this inside your .config, and if you export this folder, that is underscore scripts. Sorry, it's just, I don't know why I did that, but you can do that. So if I now go to Docker build, I have no. This, let me change, because I also have branches for my personal computer and my Ubuntu machine. Okay, so bear with me. You should get set up to this branch.
Excuse me, can you zoom in to...
Of course. Thank you for pointing that out. So, in the Ubuntu branch, you go to Docker build. So this is the one that you just need to take your shell to the folder where your Docker file is. It will call this function that creates a temporary name for your Docker based on the full path, and I'll just substitute the slashes for underscores, so it creates an ephemeral container. And then I build it with that. So all the containers that you develop in a development environment, they have different names because they are in different parts of the system. And then if you go to Docker run, this is where I'm trying to do a lot of the work to run the Docker container. So again, I do the same function so that I get exactly the same container name. I'm trying to activate mic and speakers so that I can have access to everything in the robot. User permission so that I can edit files from outside of the Docker if I'm sharing a volume. I'm adding here NVIDIA configuration, and I'm also doing X11 stuff so that I can have access to X11. So this is a configuration for NVIDIA. This allows you to run NVIDIA runtime on Docker. And this Xhost just gives like the root access from Docker to your machine. But you shouldn't use this in production, this is just development. And then I concatenate all these, like I get the container name, and the run command, and NVIDIA configuration. And then I evaluate it on the bottom. So this makes everything work nicely. So if now I go down, just put here this to scare you. I use Vim. So I install. I have a file called run.sh that is next to my Docker file. So if I now do Vim and run, I call this same script that I showed you, and I run bash, so that I can go straight to a terminal. Okay? But if now I do split and edit the Docker file, I am getting the Docker file from Mumble, ROS2, and I'm echoing this so that I don't forget the commands that I will demonstrate just now. I'm running that and I'm putting it into notes. And I am doing apt install. If you don't do apt install, if you try to install an application, the cache is completely flush, so it's like you don't have anything that you can install. So this is very important. Okay? So you need to always do apt install to retrieve the Git repo, the Ubuntu/Debian repos. And then the best program in the world, you install Vim. As you can see, it's fantastic. And then another program, which is Tmax. So Tmax is very, very important, especially when you are working and developing in a Docker container. And I will show you why. So to exit Vim, big issue for everyone, but it's the simplest of all. So it's column Q. If you do a change, it's column X. And if you don't want to save, it's column exclamation mark, and just closes without saving. But because this is the best program to exit, you can do QA, and then you exit all of them. So I don't understand the bit. You cannot exit it. But now, actually, I will show you something else. Yeah? Because I'm in a folder, I'm running Vim on that folder. I can run W to write every time I do a change. Bar. A bar is equivalent to 1%, 10%, where you can concatenate Vim operations, and then you do exclamation, and exclamation gives you access to the terminal. And I like to do clear straight out of the bat because I don't want like the previous ones to be there. And I do run. Okay? Because I did clear, I don't have anything in the terminal because it already executed. And boom, I'm in a Docker machine that has ROS installed. So if I do here ROS, I have it here. So next really important program is Tmax. Tmax is a terminal multiplexer. So you have a terminal, and this is all embedded. Like Vim and Tmax, they are embedded. So if you run Tmax, you say, what's the difference? This is like, it's multiplying your terminals. So now, if you do Control B and quotation, now you have two terminals from the same container. So you don't need any JavaScript code editor, I don't know of any, but you don't need. It's just bad.
Do you mean VS Code?
So now, oh, by the way, Vim as well, you can navigate through your system. Like you can go to folders and everything. So now you can run a listener. So nothing is happening. Is a topic is connected. Is listening for the topic in the virtual data virtualized data bus. And now I will run. So to move from one terminal to the other is Control B O, and now you are going to another terminal within Tmax. And then that's it. See guys? This is the best way. If somebody has a better way than this, please tell me. Yeah? Embedded development. We are doing robotics. We are not doing web development. This need, like we need to do like everything closer to the machine as possible because we want to extract as much performance and reliability out of it. So we cannot trust the JavaScript. It's a bad language. So I'll now exit. So then we just do exit. And you're out. Sorry. And then again, this is inception, no? I'm inside of him again. So perfect. Now the inception is over. So now I will show you how to work with Docker Compose. To be very honest, I don't have a great workflow yet. So if somebody from the audience has and wants to share, perfect. But as I said, I picked up a tutorial that you can use very, very easily if you are running any operating system that runs Docker. So you need to have Docker installed, of course, and you git clone it. You git clone this repo, and you cd into mapping, which is the program, the environment we are going to load. And then, as you saw in my personal script, you need to add this so that the Docker has full access to your computer. This is bad, but this is the way to do it. Somebody has a better way, please tell me. And now we are going to execute this. So, oh, sorry. So, oh yeah, so now before I go to that, I'm going to open the Docker Compose file for the simulation. So, this is the hard disk. This is the ROS tool that takes sensor data and displays it in a nice way so that you can know in real time what's going on. And something that is not included in this Docker file is privilege. So if you don't add privilege, the Docker will not have access to your X11 session. Okay, so you will have an error. So please come here. I'll give you permission to use VS Code if you are not using Vim yet, and just add privilege true. So, all the Docker containers in Docker Compose. So Docker Compose is not our orchestrator of Docker machines, but it acts like one. So just composes them like the same story as in ROS. So all of these containers are connected to this network. You just define the network, and the RVs, as you can see, gazebo simulation is in a different Docker container, different from RVs. Then you have the Slum tool that does like that does the mapping in real time. It's in a different container, And you have the map saver that essentially runs a bash while loop to frequently save new updates of the map coming from the mapping container. Okay? So it is sharing the volumes. In here, the slash maps in your host is being shared with the slash maps of the Docker container. So that's why when you reinitiate all these Docker containers, it's like magic. Like, oh, all this brand new Docker Compose environment knows about my maps because it's mapping it already into your Docker machine. Into your host. So your host and then the container. So it's mapping to the host. And then when you rerun it, it's just taking that. Something also very, very important is the RMW implementation. So this is the environment variable that you need to share between all the Docker containers so that they are using the same implementation of data distribution system. So this is very important. And I'm not going through the commands, but in here the display, the X11 display is here being shared so that we have access to the gazebo simulation and the NVIDIAs as well. You need to have access to NVIDIA drivers in the gazebo simulation. So this is the gazebo simulation, and this is the RVs, and both of them are using NVIDIA capabilities. So if somebody has a question, please let me know. Yeah, please. And now, see, I don't even need to leave Vim. Because that's very good. So now you have gazebo simulator in here, and then you have the RVs that is doing the real-time mapping. So this doesn't really very well.
Oh, paper? No.
These are is better. So I'm not going to talk in detail about any of these tools. I will just do an intuitive, practical exercise. And you have the control where you can move in this axis. And then you have the shift. If you press shift, you can rotate it. So you can use a combination of both to do this. So now, I will open another terminal in the same folder. So I'm in the same folder. So if I go now, I need to copy my notes. Okay, so I'm going to run this in another terminal. So this is going to execute the bash program. It's going to execute the bash program from the RV's Docker container. So I'm going to, going to run it. By the way, you need to use sudo, unless you want to type chmod 666, which is devil's number, and then you break your computer like I did. So it's up to you. So, oh sorry, what is the, I forgot. So yeah, so what we will do now, we will control this robot from the terminal, okay? So I'm going to decrease okay, I'm going to decrease just to show you. what is the command. This is the standard one that is used in the first hello world example. But I'm going to scale it down so that I can control it nicely with the different window programs, okay? And now I can, because I'm doing this on purpose so that I have, my window is focused on that, okay? And this is a bit like ASD kind of key binding. So I'm going to now control the robot using these ones. There are like 9 keys and they are exemplified there, okay? So these are the keys to moving around. And then for autonomic mode, like not from robotics, like I don't know what that is. I'll find out, because I'm contracted to find out these things. So now, as you see, I'm doing J. They should have the same key bindings as him. I need to.
Yeah.
And then I'm going to run this, and this is doing the real-time mapping. Okay. So as you can see in Gazebo, I'm going to increase and then putting the focus again on the terminal. And now you can see it clearly here. And then I'm not going through all the details about RVs because Ignacio is excellent about all of this stuff, and yeah, I think that ends my presentation and lecture. Do you have any questions, please?
Any question, anyone?
No? Please.
As the systems scale up, how does DDS handle choke points in networks? So if you've got something coming through a mobile phone network to a device, do you need the whole pipe to flow through, or just what those the channels are subscribing to?
So to connect something that is outside of DDS to DDS.
Well, do you need to run a bridge, or can you run DDS to something smaller?
Sorry, I'm not listening.
Sorry. Do you need a bridge to do that, or can you still have it connected to DDS without having the entire pipe needing to go across that slow connection?
Okay, thank you. That's a good question. I'm not yet an expert in data distribution service, but I can tell you if you want to communicate a DDS, for example, with your phone or any other device, you can use like HTTP request to do that. But if you want, you can also communicate from the phone to an embedded system that is connected, and then it will communicate with the robot. So we have a lot of flexibility in terms of communication, and then it comes up, it goes down to the developer to find out what is the best solution. But yes, if the device is connected to a connected DDS, one that is connected with the robot, you can connect through DDS to the robot. Otherwise, you can use like any other, you can use any, for example, ROS service. That, for example, in C++ or in Python, there is lots of tools to do HTTP requests, so you can do it that way. But that comes down to what are the advantages and disadvantages that you value the most. Yes, but that's a really great question. Thank you. Anyone?
Yes. Question, yeah. Do we have any robots running ROS2 in the robotarium, or they all still with ROS1?
Yeah, the robotic, the big car.
Oh, the big car? Okay.
Yes. So it's good. Yeah, we should go and try it, definitely.
Because they were asking me why I'm not teaching the class with ROS2 and outside world. It's like we need a little bit more, to be sure that we have everything running. ROS2 basically before you take the step to the class.
Exactly. But there are more. I think like ROS1 or something else. I don't know. But there are.
I don't know if they have ROS2 already.
Sure. Okay. So if you don't have any question, but please find one.
We'll say thank you again for